So in this lesson, I'm going to talk about the monic polynomials. So what do we mean by monic polynomial? Now, a polynomial of degree n is said to be monic if the coefficient of x power n is 1. So if we want to know, or if we are given a polynomial, we want to determine whether the polynomial is monic or not, we just need to know the degree of that polynomial. If the degree is 3, for example, then we check the coefficient of x power 3. If the coefficient is 1, then we know the polynomial is monic. If it is not 1, then the polynomial is not monic. And we are talking about positive 1 here, not 1 in magnitude. So if it is negative 1, then the polynomial is not monic. So we have two examples here. P3 of x power 3 plus 4x squared minus 3x plus 6. If you look at this polynomial, we see that the highest power of x is this one, x power 3. Then, so this is a polynomial of degree 3. Then we ask ourselves, what is the coefficient of x power 3? We see that the coefficient is 1. And therefore, this polynomial is monic. If we look at the second one, we look at the terms here, and we see that the highest power of x is 4. So this is a polynomial of degree 4. Then we check what is the coefficient of x raised to power 4. The coefficient of x raised to power 4 is 5. And because the coefficient of x raised to power 4 is 5, then the polynomial is not monic. The polynomial is not monic. Now, note that any polynomial Pn of x of any degree n can be converted into a monic polynomial by dividing the coefficient of the leading term. By dividing the polynomial by the coefficient of the leading term. So if we have a polynomial, say, if we have a polynomial which is not monic, say we have p4 of x is equals to say x power, let me start with x power 4. So we have 5x raised to power 4 minus 8x squared plus 3x plus 1. This is a polynomial of degree 4, and it is not monic because the coefficient of x raised to power 4 is 5. So we can generate another polynomial. Let me just call it f of x for now. And we define it as 1 over 5 times p4 of x. So this means that we divide each term here of this polynomial p4 by 5. So when we do that, the first term here, when we divide by 5, will give us x raised to power 4. The second term will give us minus 8 over 5 x raised to power 2. The next term will give us 3 over 5 x raised to power 1, and the last term will be 1 over 5. Now, the polynomial f of x now is still a polynomial of degree 4. It's still a polynomial of degree 4, but the coefficient of x power 4 is now equals to 1. So this one is a monic polynomial. F of x is a monic polynomial. P4 of x was not monic. But when we generate another polynomial, f of x, by dividing p4 by 5, which was the coefficient of x power 4, we get a monic polynomial. So basically, in a polynomial Pn of x of degree n can be reduced to a monic polynomial by dividing each term of the polynomial by an, where an in this case is the coefficient of x raised to power n. We have an example here. The polynomial p4, which is defined by this, can be reduced to monic by dividing each term by the coefficient of x raised to power 4. This coefficient happens to be 5. So when we divide, we get another polynomial, which is now monic. Now, for the notations, we are going to use, we are going to write Pn of x and use a symbol tilde to denote the monic polynomial. So we write, given any polynomial, we shall write that given any polynomial Pn of x, then we have a monic polynomial Pn of x. The associated monic polynomial Pn of x tilde is obtained by dividing Pn by a raised to power n, where an is the coefficient of x raised to power n. A subscript n is the coefficient of x raised to power n. So this polynomial is now a monic polynomial. And it is important to note that if we know the roots of Pn of x, and then divide Pn by an, if we know the roots of Pn of x is equals to 0, and then if we have an equation such as this, then we generate another equation, Pn of x divided by an. An is a constant. This will be just equals to 0 again. So the roots will be the same. The roots will not change. For example, we know that the roots of x squared minus 5x plus 6 is equals to 0 are x is equals to 3 and x is equals to 2. We know these are the roots of this equation. Even if we divide this equation by 3, for example, or by 4, and we write 1 over 4, x raised to power 2 minus 5x plus 6 is equals to 0. Even if we divide this equation by 4, the roots will not change. They will just remain the same. The only thing that can happen is that the turning point might be affected, where the curve looks like, for example, where the curve looks like that, and you have the roots at this point here, which we can call x0 and say x1. These are the roots. Then we have the turning point here. The turning point will be affected in such a way that when we divide this function by 4, say if our equation was y is equals to f of x, and we define another equation by as y1 is equals to 1 over 4 of f of x, we say that each value of f will be divided by 4. So the point here will be shifted downwards. So while the root will remain the same because 0 divided by 4 is still 0, any other point will be affected and it will shift downwards, so that the turning point will now not be where it was, it will be shifted downwards, like that, for example. So the turning point will be shifted downwards here. If for example, we have a curve which turns again, say we have a curve which turns twice, and we have 3 zeros or 3 roots, then this one will also turn again and pass through that point. The turning point here will be shifted upwards. The minimum point will be shifted upwards. The maximum point will be shifted downwards. So when we generate a monic polynomial, it will have the same roots, the same points as turning points here, say A and B. If this were the turning point, they will remain the same. But the value of y, the maximum value, the minimum value here will be shifted. The minimum value will be shifted upwards by a factor of 4. If we are dividing by 4, the maximum point will be shifted downwards here. So basically, we want to look at the Chebyshev monic polynomials. We had looked at the Chebyshev polynomials, and we had seen that the Chebyshev polynomial Tn of x could be expressed as 1 over 2 raised to power n minus 1. Sorry, this is not correct. We could write 2 raised to power n minus 1, then Tn of x. Sorry, I'm making errors here. The first term is x raised to power n. Then we have the other terms. The coefficient of the highest power of x was 2 raised to power n minus 1. That's what we had seen. So it means that we can generate a monic Chebyshev polynomial by dividing Tn of x by 2 raised to power n minus 1. We divide each term. So when we do that, T naught was equals to 1. So that one is just equivalent to the corresponding monic polynomial. But for n greater than or equals to 1, we can write 1 divided by 2 raised to power n minus 1, Tn of x, to generate the Chebyshev monic polynomial. Then we had the recurrence relation. The recurrence relation which we have here. This relation will reduce and be reduced to this form. T2, the Chebyshev monic polynomial T2 is equals to x times the Chebyshev monic polynomial T1 minus T naught x. Then for n greater than or equals to 2, we have this. And as we had seen, we can see that because the Chebyshev monic polynomial is a constant multiple of Tn, we are just dividing Tn by 2 raised to power 1 by 2 raised to power n minus 1. So the zeros and the extrema of the Chebyshev monic polynomial are the same as the zeros and the extrema of the Chebyshev polynomial. So the zeros of the Chebyshev monic polynomials are still the same as we have obtained for the Chebyshev polynomial, while the extremas are still the same. But now, when we talk about the maximum point or the minimum point, their values will be reduced in magnitude by a factor of 2 raised to power n minus 1. So we had seen that for the Chebyshev polynomial, the maximum and the minimum points, the values of the maximum and the minimum point were defined by minus 1 raised to power k. So we'll just be dividing this by 2 raised to power n minus 1 to get the associated maxima and minima. So anything else remains the same. So we look at theorem 4. We had looked at theorem 1, 2, and 3. So we look at theorem 4 here. Now the polynomial Tn of x tilde, the Chebyshev monic polynomial for n greater than equals to 1, has the property that 1 over 2n minus 1 is equals to the maximum absolute of the absolute value of Tn. n of x, the monic Chebyshev polynomial in the interval -1 to 1. And this one is less than the maximum of any other polynomial in that interval. So the Chebyshev polynomial has the minimum maximum absolute value in the interval -1 to 1. Now, pi n here is the set of all monic polynomials. And the equality sign here will hold only when Pn of x is equals to the Chebyshev monic polynomial. Now, this theorem implies that the Chebyshev polynomials, the Chebyshev monic polynomials here, this is the Chebyshev monic polynomials, have the minimum maximum absolute value that is spread uniformly on the interval -1 to 1. And this is an important property that is usually used in reducing the degree of polynomials when we want to do interpolation or extrapolation. That is, when we want to do an approximation, we can use this property of the Chebyshev monic polynomials to obtain a polynomial of lower degree that can be used in approximation. So we look at this application, reducing the degree of approximating polynomials. Sometimes we call this the economization of the Chebyshev polynomials. So from the theorem 4 here, above here, Chebyshev polynomials have the minimum maximum absolute value that is spread uniformly on the interval -1 to 1. And this property of the Chebyshev polynomials can be used to reduce the degree of an approximating polynomial with minimal loss of accuracy. We consider the problem of approximating an nth degree polynomial of the form Pn of x is equals to a0 x raised to power n plus a1 x raised to power n minus 1 plus a2 and so on up plus an. This one, there is another here, this one should be plus a2 x raised to power n minus 2, like that. We want to approximate this with a polynomial of at most degree n minus 1. So we want to reduce the degree of this polynomial by 1 and obtain a polynomial that best approximates this. So the problem at hand here is to choose a polynomial of degree n minus 1 from the set of all polynomials of degree n minus 1 that will make the error in the approximating the Pn a minimum. The error is the maximum error in that approximation will be the value of Pn of x minus the value of the polynomial that we choose. So if we can make this as small as possible, then we shall have the best approximating polynomial. So we note that when we subtract Pn minus 1 from Pn, when we write Pn of x minus Pn minus 1, sorry, Pn minus 1 of x, we get a polynomial of degree n. We get a polynomial of degree n. Why do we say that? When we have a polynomial such as P3 of x is equals to, say, 2x raised to power 3 plus 4x squared minus 8x plus 2, for example, and then we get a polynomial of degree 2. So I have 4x squared plus 5x minus 2. And suppose we get the difference between these two. You see, the leading term here will remain. It will not be affected by this difference. So we shall still have, when we write P3 of x minus P2 of x, we shall still have 2x raised to power 3 minus. Now, in the next term, this is where we can have 4x squared minus 4x squared, or whatever the value is here. Then then we have minus 8x minus 5x, then plus 2 minus 2. So, but you see this, for the leading term is not affected by this difference. So the leading term remains the same as it was. So if P3 was a polynomial of degree 3, then P3 minus P2 will still be a polynomial of degree 3. And the leading term will not be affected. The coefficient of the leading term, again, will just remain the same. So we can generate a monic polynomial here by dividing this. You see, if we take now this and divide by 2, which is the coefficient of x power 3 in P3, we shall get a monic polynomial. We shall get a monic polynomial if we divide by 2 here. So we are saying, we note that 1 over an times the absolute value of Pn of x minus Pn minus 1 of x is a monic polynomial, and therefore by using theorem 4, the maximum of this polynomial in the interval minus 1 to 1 must be greater than or equals to 1 over 2 raised to power n minus 1. And remember, this quantity is equals to the absolute value of the monic polynomial, monic Chebyshev polynomial, the maximum of the absolute value of the monic Chebyshev polynomial as per theorem 4. So this equality will therefore hold only when this polynomial here, only when this polynomial that we are generating here is equals to the Chebyshev monic polynomial. Now, with this relation here, if we multiply both sides by a raised to powers, by an, if we multiply both sides of this by the coefficient an, then we can get this relationship here, which we rearrange to make Pn the subject. Pn, we want to make Pn minus 1 the subject because we want to find a polynomial of 1 degree less than that of Pn. So we get Pn of x minus a times an times the Chebyshev monic polynomial. So we get that. So this will give us the best approximation for the polynomial of degree n minus 1. This equation, which we call equation 8 here, is especially useful when we want to reduce the degree of an approximation polynomial with minimal loss of accuracy. We call this process the Chebyshev economization. We want to look at an example of Chebyshev economization, and we shall just use this equation 8 here. So you are given a polynomial of degree 4. So you have to use a Chebyshev economization to find a polynomial of degree 3 to approximate the function below this function on the interval minus 1 to 1. And we shall use equation 8. We want to get a polynomial of degree 3 that can be used to approximate this. This one is a polynomial of degree 4, so we can call it P4 of x. So we see that n is 4. So in this equation 8, we put n is 4. So n minus 1 will be 3. Then Tn. This will be T4. So from equation 8 with n is equals to 4, we shall get this equation. And remember we had obtained T4 of x as 8x raised to power 4 minus 8x squared plus 1. So we can get the associated Tn, T4 of x, the monic Chebyshev polynomial, by dividing this by 4. By 8, sorry, not 4. If we divide here by 8, here by 8, here by 8, so we get the Chebyshev monic polynomial of degree 4, which is this one. So P4 is the function that we have been given here. E4 is the coefficient of x power 4, which is 1 over 15. So A4 here is 1 over 15. So we shall multiply T4 by A4, which is 1 over 15, and subtract the result from A4. That will mean that the last term here, x power 4, will vanish. So we substitute. We get this. And now we say that we'll be having the first term will be 1 minus 1 over 15 times 1 over 8, which is 1 over 120. The next term we have minus x over 2. We don't have x power 1 here. So that term will just remain x over 2. But we have x over 5, and we have x squared here, and we have x squared. This is x squared all over 5. The other one will be minus 1 over 15 minus x squared. That will give us plus x squared all over 15. Then for the degree 4, this one was degree 4, sorry. This one was x power 4, not 5. So we shall be having x power 4 divided by 15 minus x raised to power 4 divided by 15, and this will be 0. So you need to work out this quantity here, and this one. The last term here is 0. Now x power 3 will just remain x power 3 over 4. So we get 119 over 120 minus a half x plus 4 over 15x squared plus 1 over 4x power 3. This is now a polynomial of degree 3, which can be used to approximate the polynomial of degree 4 here with minimal loss of accuracy on the interval minus 1 to 1. We can do another example. We have the function f of x is equals to cosine of x. It's approximated on the interval minus 1 to 1 by the 6th degree Maclaurin series we have here. This is the Maclaurin series approximation using the first 4 terms. We want to use the Chebyshev economization to obtain a polynomial of lower degree to approximate this function. Now, we shall use equation 8. Where is equation 8 here? And set n is 6, because the polynomial Pn there is of degree 6. So we set n is 6. N minus 1 is therefore 5. So with that, we shall have P5 of x is equals to P6 of x minus A6 times the Chebyshev monic polynomial T6 of x. Now, A6 is the coefficient of x power 6 here. So A6 will be minus 1 all over 720. P6 is this polynomial here. So P6 of x will be the polynomial 1 minus x squared over 2 plus x raised to power 4 over 24 plus x raised to power 6 over 720. This is minus. The last term here is minus, not plus. This one is plus. So that is P6. But what is T6? The monic polynomial T6 can be obtained. We can generate the monic polynomial T6, and this is given by x power 6 minus 3 over 2. This one can be obtained from the recurrence relation. So we have x raised to power 6 minus 3 over 2 x raised to power 4 plus 9 over 16 x squared minus 1 over that 2. So when we substitute back, notice that a6 is negative here. It is very easy to make an error here. a6 is negative, and we are subtracting. So we will be having minus minus, which will be plus. So we have the polynomial P6 here, then minus minus a6. So that will give us plus 1 over 720, then Tn of x here. And then we can put the right terms together. 1 plus 7 plus 1 over 720 times negative 1 over that 2. That will give us 0.999566. Then we have minus x squared over 2 plus 1 over 720 times 9 over 16. And that should give us minus 639 over 1280 x squared. Then we have x raised to power 4 over 24 plus 1 over 720 times minus 3 over 2 x raised to power 4. That should give us 19 over 480 x raised to power 4. Then we have minus x power 6 over 720 plus 1 over 720 times x raised to power 6. That will give us 0. And so we get a polynomial of degree 4. Get a polynomial of degree 4. And this one we can use it now to approximate the polynomial P5, P6 here that we have been given here with the minimal loss of accuracy. So I think I'm going to stop at that for now. We shall look at something new in the next lesson. Thank you for this, and just try to work out these problems again. And make sure you follow each step. Make sure you can follow each step here. Don't just don't just listen to the video. Take the polynomial and work it out yourself. See that you can get the results as we have obtained here. Thank you.